In this video, we're going to discuss some of the finer points about understanding when a vector field in the plane is conservative on some region. I've drawn 3 boxes here, and I'm interested in how the concept in each box is related to the other. At the top, I've put in a vector field F, and I've stated that it's conservative on some region R. That means it's the gradient of some function phi, so the potential function phi. It's a consequence of the fundamental theorem of line integrals that the conservative field must also be path independent on that region. Path independent means if you calculate the work done by that field along any path in the region, the value of that integral is only going to depend on the endpoints of the path, and therefore is independent of how you chose to get between those 2 points. In the previous video, we looked at the curl of the field, and we saw that if the vector field was conservative, then it must be curl-free on the region. That is, the curl is 0 everywhere on R. Under reasonable conditions about the region R, the converse statements hold. So under reasonable conditions about R itself, if it's path independent, then the field is conservative, and if the field is curl-free, then the field will be conservative. Those conditions on the region R, which is some subset or some space on the plane, are called topological conditions. Topology in mathematics is a branch of mathematics that studies the structure of space and gets at some of the more qualitative features that you recognize when you look at a figure in the plane or some sort of geometric shape. In this instance, the conditions that we require about this region R is it must be open, and I'll explain what that means in a minute. It must be connected. Again, I'll explain what that means. And it must also be what's called simply connected, which is different than being connected. So it must be open, it must be connected, and it must be simply connected. If these 3 conditions are met, then I can guarantee you that the converse holds, that those arrows above are reversible. And we'll state a theorem in a minute that if my region is open, connected, and simply connected, that everything in these 3 boxes are all equivalent statements to one another. So let's discuss a little bit about the topology of my region R and these 3 conditions. Let's talk about openness first. So in the plane here, I have drawn some region R, just some blob of points in 2 dimensions. And when I talk about openness, what I require is that the set that I'm looking at doesn't contain any boundary points or any edges. That's still very vague, so let's be a little bit more precise here. I'm going to look at a point in that region. There's a point right there. That point, it looks like it's sitting in the inside of that region. What I mean by that is I think I can find a little disk around it where it's at the center, that I can make it small enough so that disk lies entirely in my region. That's good for being open. On the other hand, if I go to a point right here on the boundary of this region, right here on the edge, and I draw a little disk around it, no matter how small I make that disk, there will always be some points that are in the region and some points that are outside the region. No matter how much I shrink that disk down, it looks like there will always be these points hanging over the edge, not in R itself. That's not allowed for an open set. What we would need to do in this case is delete all the points around the edge, and if I was just to remove those and just keep those points in the interior of the region, then it would be an open set. So for the theorem that we're going to state, it's going to require that R is open. We can't allow any edges to the set if we want the theorem to be sure that the theorem is true. The next thing is connectedness, and this is very straightforward for us in this class. Here I have a region R. This region is connected as I've drawn it right now, because if you pick any 2 points, I can draw some continuous curve connecting those 2 points that stays entirely in my region. So this region here we would say is connected. If my region included some other part, some island over here, so my region R is this area here and this one here, it's clearly now not connected because there is a point in this set and a point over here that could never be connected by a continuous path. without leaving the region R. So currently now it's no longer connected. Simple connectedness is a little more subtle. Here I have a region R in the plane, and right now it is simply connected. Simply connected is roughly saying that there's no holes in the region. And one way I can detect whether or not there's a hole in the region is to look at a loop in the region. Here's a little loop, a closed path, and I'm pretty sure that I can take that closed path and I can continually draw it down, contract it, shrink that loop down to a single point. So just imagine kind of contracting it continuously in one direction, drawing it down to a point, and if I do that, I will never have to leave the region R to accomplish that. No matter what loop I drew in this region R, I could always contract it entirely within R down to a point. This region here is simply connected as a result. However, if I had a region that included, that looked pretty much the same, but I deleted all this stuff in the middle here, and I put a hole in my region, this is now no longer simply connected. Way to detect that is there's this loop here that I can draw around that hole. And no matter how hard I try, as I try to contract that down to a point, I'll eventually have to wrap it around this hole, and to continue the process of contracting it down to a point, I'd have to leave the region R to do so. So this is simply connected here, no holes in it, all loops contract continuously down to a point. This space here, not simply connected, there's a hole in it, and therefore not simply connected. We're ready now to state our theorem. Suppose that F is a vector field in the plane on some open, connected, and simply connected region. Then the following statements that I'm about to write down are all equivalent statements. I'm just going to say that very quickly by saying TFAE, the following are equivalent. I'm going to make a list. If one of those things in the list is true, everything in the list is true. And if one of those things in the list is false, everything in that list is false. And the first thing at the top, of course, is being conservative. So F is conservative. What does that mean? It means F is equal to the gradient of some potential function for some function phi, which is defined on my region where I'm considering. The next thing is that F is path independent. Another interpretation of path independence is that if you go around a closed loop, no work is done by that field. And we've seen this before, that if F is a conservative field, then it does no work around any closed path in R, a loop. And then finally, 4, this is really the one that's most interesting to us from a computational standpoint, F is curl-free on that region. In other words, if curl of F is 0 everywhere, and your region satisfies these topological conditions, you can conclude that it is conservative.